I'm gonna go ahead and get started. How's everybody doing today? Everybody feeling all right?
A little done today.
A little done
I don't know.
over the fact that this week is not finished yet.
Yeah. I don't know. I was like exhausted by Tuesday and never really recovered.
Yeah, I was exhausted by 2019.
Oh no.
But I feel you, man. Sometimes weeks catch up. So okay, today we're going to be talking about, we're going to finish up what we were just talking about on Wednesday. We're going to talk about color and black body, and we'll talk about magnitude again. The first thing I'm going to do is run through the homework set. Okay, so there were two homeworks that I assigned. And most people, everybody did the first one and not everybody did the second one because I had two numericals that were due on the same day, but that wasn't necessarily clear. So I moved the due date of the one that a lot of people didn't do to Monday. That's okay for me. So there's a numerical due Monday if you didn't do two today, which is, fire up the notebook and then we'll talk about it. And this is 2, we'll talk about 2. So, if you didn't do the second one, freebie, and also I'm going to go over it too, because I'm going over things right now. Okay, so this homework set, you got to go away. Oh, you're over here. I'm lost desktops. I'm going to come over here. No, not over there. So, this homework set starts off with this cell that has a bunch of stuff in it. So Python likes these modules, so it starts with these import lines that just says we're going to use this package called NumPy and we're going to call it NP. That's just shorthand. I can call it whatever I want. NP is very common. And then matplotlib will import as pyplot, as we'll call this PLT, and we'll do all our plotting with this. And then this line just makes it so that the plots show up like when you hit go. And then this is a big wad of physical constants so that you don't have to go look them up. We're going to need those as time goes on. So problem 0, so this homework set was really about just getting your hands dirty with plotting and with making functions. So the first two problems were just do some little things to make sure that you get those going. And you know how the basic machinery works. And then there's one problem with actual work in it. So the first question is write a function to return a black body. And this here I wanted to take a wavelength and a temperature, because a black body is a function of temperature and it has to do with wavelength. It gives you the wavelength distribution. So you need to take a wavelength and a temperature. We want to use CGS because that's what astronomers do. And then you type carefully. And then plot it for a couple of temperatures. So let's see. This is from one of you, but it looks pretty much like everybody else's. So your function should look something like this. We need def, just says we're starting a function, and then the function name here we've called it black body. And it takes L, a wavelength, and K, which should be a temperature.
Temperature in Kelvin.
Temperature in Kelvin, yeah. Okay. I stole this from him. Mostly because I had accidentally deleted my version, and I was like, oh crap, I need to get the right answer. So your lin space goes like this. So this is the array of wavelengths that we want to use, that we're going to plug into our black body. So this goes from 10 to the minus 7 nanometers or this goes from 100 times 10 to the 7 centimeters to 10,000 times 10 to the minus 7 centimeters, because that's how you convert centimeters to nanometers, and we'll have 10,000 points in our line. And then Ks, this is our range of temperatures. This goes from 3,000 to 5,000, and there's 6 of them. Now, in this black body, here's a very common mistake is to try to put in a vector in both of these. Python is very smart, or relatively smart. Really, NumPy is relatively smart in that if you start dealing with arrays, then it will just treat them as though those are variables that have arrayness to them. But if you do 2, then you have to be very careful about how you do it so that you get the right answer. So what you need to do is loop over temperatures and then plot your black body. So the way this works is for I in KS, so that's going to take KS, which is this list of temperatures. Just go through everything in this block and replace I with KS and then repeat everything in the block over and over and over. So what that does is it calls plt.pyplot, and the first element is the x-axis, which is the length, which is the wavelengths, and the second element is the y-axis, which is the thing that you just made, and it takes the wavelengths up here, and I, which is a temperature here, and then you get something that looks like this. Most everybody got something that looks reasonably like this. If you didn't, I'm going to put the solutions up later today. If you didn't get something that looks like this, go back and see what you did wrong. Yeah.
Could you label it also in the for loop?
Yeah, sure. You can do.
Is it okay if it was like really not that smooth, like a lot less smooth?
Yeah. What makes it smoother or not smoother?
I don't know. It was just very blocky.
So here's our loop.
I think I just didn't have as many points. Yeah, that's what it looked like. Oh.
So you don't have as many points, so you're only sampling. Here, let's make this a scatter instead. Actually, we'll add a marker on this so that you can see the points. So if you only use 100 points, then you get something that's real wonky looking. You can see that it's just a straight line between the points that evaluates. And then you can label them. Let's say I. Actually, we could do this. D Kelvin. You need to type a legend to make the labels show up. And then it shows up like that. Now we have labels. None of that's strictly necessary, and I graded this one already, and you'll notice that you got all the credit, regardless of what you did. So even if you screwed it up and didn't go to what I want, my goal here is: did you put in the grind? Did you go try it? Did you put your hands on the thing? And even if you didn't get what I got, did you at least put your hands on it and get some of those? That's all I was looking for. Does anybody have any questions about this? Everybody happy? Okay, I'm going to go over the other one that isn't due yet. So Merry Christmas. Yeah, I moved the due date this morning. A lot of people do that. So if you've done it already, you're set. Now I'm just gonna, so for the half of you that did it, I'm just going to go over it. For the other half of you who didn't do it, I'm going to go over it. So this one has a couple of glitches in it. So we start off the same way, but now we have this star data main sequence.h5. And one thing that threw off a whole bunch of people was they tried to click on that file, and then that stopped the work, because if you can't click on that file, it doesn't do anything. You read that file here, so that's what this thing does. So I need to make sure that I put that in the instructions next time, because you don't need to click on that file. The notebook will take care of opening it. The notebook knows how to open it. So this little bit of code. So we start off with the same kind of things. The physical constants are here because I didn't need it this time. But then we have this new block of code. And what does it say? It says import h5pi. h5pi is a data packaging package. So all it does is it takes your data and it makes it binaries. So f pointer is h5pi.file, my file name, and then r for read. If you change this to a w, you'll totally jack up your homework, and you'll put like the homework data set. So don't touch this. So what this does is it opens up a file and calls it file pointer. And then it makes a dictionary. Remember from the first assignment that curly brackets make dictionaries. So this makes a dictionary, and then it assigns this, it loops over everything in the file pointer. So in file pointer.keys, this is everything that's in the file. It assigns star data square bracket field to whatever it gets out of the file. Now, I don't expect anybody to actually reproduce this code. I'm just going over it so that you see what it does. All it does is it reads this file and puts it in a dictionary that we can get stuff out of. So then you can get out what the values are in that dictionary with stardata.keys. So a dictionary is just a relationship between words and things. So I have this thing, and I hand it words, and it hands me back things. So I hand it, for instance, absolute bolometric magnitude, and it will hand me the absolute bolometric magnitude for a bunch of stars on the main sequence. So what this does is it gives me lists of things on the main sequence that I can play with. So number 2 is make an array b minus v and add it to b minus v, and then make an array with the bolometric magnitude. Bolometric just means all of the light. I'll explain what that is a little bit later today in a little more detail. And then plot, and this should work. Why did that not work? It didn't run the first one. Work, there you go. And you will work. And then it'll get you these two curves. So the first curve is the absolute magnitude, and so that's the absolute magnitude as though the star were at 10 parsecs. So to get the star as though it were at 2 kiloparsecs, we do the following. So where's my eraser? And chalk. All this pink chalk is so weird. But it's just the pink chalk and dust. What was that? Oh yeah, so we're going to use the basic definition of a magnitude. M1 minus M2 equals minus 2.5 times the log of the flux of 1 over the flux of 2. Does that make sense? This is just definition. It doesn't need to make sense. You just have to believe me that this is the definition. And we plug in different things for M1 and M2 and F1 and F2 based on what we need to get out of outer space. So if I have 2 stars, and they have the same intrinsic luminosity, but they're at different distances, then I would say, if I've got, so here's me, here's star 1, or let's call this star 2, let's call this star 1. They're the same star, so they have the same luminosity. I'll tell you how to get the luminosity in like 11 seconds. But they have the same luminosity, but they're at different distances. Then we could say that M2 equals M1 minus 2.5 times the log base 10 of the luminosity over 10 parsecs squared divided by the same luminosity over 2 kiloparsecs squared. Everybody follow what I did there and why? So I have I have the same star twice. So I've got it at 10 parsecs, that's its natural magnitude, or that's its absolute magnitude. And then I want to know what its brightness would be at 2 kiloparsecs. Is that a question, or is that?
No,
so then we just do this algebra. We'll just simplify this algebra. So the L's cancel out. These are both 1 over, so it flips over and gives us a minus sign, or it gives us a minus sign. And the 2's can come down. So this turns into a, let's call this minus 5 times the log base 10 of 1 over 10 parsecs, the square is gone, over 1 over 200 parsecs. We'll rearrange this and we get minus 5 times the log base 10 of 200. Is that right? Does that make sense? And what's the log base 10 of 200? It's like 1 point. It's like 11. 12. So does that make sense? So this is the thing that you add on to. So I've given you this. I want this, so you just have to add this.
Oh.
Does that make sense? All right. If you've turned it in already, I haven't looked at them, so go ahead and turn it in again. Okay. That is, and that's it for that homework set. So now, I want you, and I'm gonna close you. Oh, no, you're not on the right screen. There you are. Okay, so what's next? Okay, so businesses. N2 and N3 are due. N3 I pushed to Monday. Several of you have asked me about the midterm next week. Yeah. It was only a midterm. There was only a midterm next week before the semester started when I was writing the schedule and I put it in the syllabus. Don't look at the schedule in the syllabus. It's totally fucking wrong. It's a lot wrong because there was a hurricane and it totally jacked everything up. So so we'll have a midterm in 2 weeks. So we'll have next week. We'll talk about magnitudes, or we'll talk about binaries and quantum mechanics. And the following week, we'll talk about stellar spectra. And then the week after that, we'll have a midterm. And the way that'll work is we'll do a midterm prep on Monday, the 9th. There will also be a homework due then, so we'll go over the homework and review everything for the midterm. Then we'll have the midterm, and then on Wednesday, and then we'll talk about it on that Friday, the 13th. Does that make sense? There was a reading due today, but I'm not going to get to it till Monday. So if you didn't do it, we finish it up Monday. Okay. So now I'm going to go through black bodies, filters, colors, and magnitudes. But I'm going to real quick go through all the questions. These are just the notes that I already said. So I want to real quick go through the questions so that I make sure that I cover everybody's bases. Let's see, I talked about ENB. I didn't talk about polarization. So polarization, I'm going to talk about it very quick. A photon has an electric field and a magnetic field, and they're perpendicular to the direction of propagation. So the photon is going this way, the electric field is going up and down, and the magnetic field is perpendicular to that. Now, if I line up all of the electric fields from all of my photons, then I have polarized light. If I have my polarization direction from all of my photons is going in random places, then I have unpolarized light. You got to do something to make the light polarized, and you can reflect it off a surface or run it through a screen with vertical gratings. There's lots of ways you can polarize it. Polarization is super fun and cool, but I'm not going to need it for this class. So pointing vector, no. Everything has a radiation pressure. I answered that one. The bolometric correction, I'll show you in a second. We're going to talk about luminosities in various bands, but that's different from all of the stuff. So when I have a black body looks like this. This is wavelength. Let's call this the visible light here. The light that I'm going to see is just in this band. So say for instance this is the sun, and I drew it correctly so that the peak is actually a green or something. This is the visible light, but the bolometric light is everything. So if I'm going to express this as an integral, if I want to look at just the visible light, and I want to know what the luminosity in the visible is, I'm going to integrate the black body. We're just going to call this B of nu of t. Actually, let's call it lambda, B of lambda of t. Lambda equals lambda 1 to lambda 2 d lambda. That is the visible luminosity. I just integrate from one wavelength to another wavelength, and I get just the visible luminosity. But when I'm doing physics like I'm going to do in a second, that's not the luminosity that matters. The luminosity that matters is the bolometric luminosity, and that's the integral from 0 to infinity of d lambda of t d lambda. So I integrate everything under the curve, and that's the bolometric luminosity. And so but I can't measure that. There's no telescope in the world that can actually measure the bolometric luminosity. Why is that?
Because
No, it's
because we cannot measure the entire spectrum.
spectrum?
Yeah, because we can't measure the whole spectrum with one object, because this over here is in the radio, and this over here is in the UV, and this over here is in the X-ray, and the X-ray is really difficult to focus. So bolometric means all of it, and we need to correct for it by doing some math that I'll show you in a second. Maxwell's, I talked about them, but we don't need them. What are apparent and absolute magnitudes, and what's the difference? So I have this sheet that, if they're not online, they'll be online soon. I'm gonna pull this up. I'm just gonna run over this. So these are the slides that I wanted to be working off of yesterday, spaced. So, so, okay, so this is, here's soup. Here's sorted soup. Here's a salad. Here's assorted salad. So the reason I put up the soup and the salad is because they're funny. But the artist also did it with stars, which I love because he took this star field and then he sorted them. And this is the initial mass function, or not the initial mass function, it's the current luminosity function. But this is what Hipparchus did. Hipparchus just said, I've got all these stars in this bin, all these stars in this bin, all these stars in this bin. We're going to call this one 1, 2, 3, 4, 5, 6, and I can't actually see this.
Why isn't that entirely arbitrary though in the first place?
1, 2, 3, 4, 5, 6?
Yeah, but like you chose, like, why did you only divide it into 6?
Because that's what he could tell.
But
I mean, we could fight with Hipparchus all the time, but why did he make it upside down? That's the thing that sucks.
oh,
Because a brighter star has a smaller number. That's the thing that really sucks. Anyway, we can complain about this all day, but we're kind of stuck with it. Okay, so magnitude in general. A magnitude in general is m1 minus m2 is minus 2.5 times f1 over f2. The apparent magnitude, f2 is a fiducial star that we test, and m1 is what I actually measure. For the apparent magnitude, m1 is the apparent magnitude, and m2 is the absolute magnitude. M1 is the absolute magnitude, which is if we're at 10 parsecs, and m1 to m2 is the apparent magnitude, which is what you measure. So then the flux is going to be the flux at 10 parsecs versus the flux at its own parsecs at its actual distance, and the fluxes cancel out, and this whole f1 over f2 just turns into the distance, or the log of the distance. I'll do that again in a second. Then we define this thing called the distance modulus, which is the difference between the apparent and the absolute magnitude, and it's the log of the distance, which looks a lot like the absolute magnitude. It's really the same thing, we're just rearranging things. But I can't measure the absolute magnitude. I have to know what that is, but I can measure the distance modulus, and then I get the distance from that. The other thing we need to talk about is the color index. We'll talk about that today. So I got this big sheet here where I organize everything that looks like a magnitude. I think it's everything. There might be one that I'm missing. So the apparent brightness is what you actually measure with the telescope. Actually, let me put that up there. Did I do it all? So the B band brightness is just like the apparent brightness, but only for the B flux. What is that? I'll come back to that in a second. The absolute brightness is not something that you can measure, so writing it down this way doesn't really do you a lot of good, unless that's the thing that you're asked for. But the absolute brightness is the thing that we need to compute, and that's what we'll compute today, or maybe for the homework, probably both. So we'll compute the absolute brightness for some objects. And then you use that to get the distance modulus. The distance modulus is actually much more important than this definition here. The distance modulus is what I measure minus what I know that thing to be. And that gives me the log of the distance. Does that make sense? Color index. Let's talk about color. I'm going to talk about black bodies for a second, actually, before I talk about color. I'm going to spend another minute on it. so I started to say some of this, but I'm gonna say it again. So a black body is the distribution of the number of photons versus wavelength for the thermal energy of an object. So that means only the thermal motions, not anything else. So if the thing is being destroyed, if it's on fire, if it's undergoing some phase transition, like it's boiling, or if all of the atoms are de-exciting, or if it's in an excited state and becoming a not excited state, none of those things are black bodies. All those are something else. A black body is only the thermal radiation from a thing with a temperature that's pretty much in equilibrium. Okay, I say pretty much because we're astronomers and it's really hard to do things right. So we wave our hands and say, I hope that that thing's in equilibrium. It's got to be in equilibrium for the black body to actually make sense. So fire is not a black body because fire is not in equilibrium. Fire destroys the thing, right? Just like the nuclear burning at the center of the sun. That's not in equilibrium either, but that's far away. We don't see that. What we see is the hot gas that thing heats up. So the thing that you heat with fire makes a black body, but the fire is not a black body. Means no line radiation, no transitions, and only photons from the object, no reflections. So that's kind of a given. If I want to know what this thing is doing, I don't want to know what this other thing that's shining on it is doing. That doesn't help. Those are the necessary things for making a black body. I want to close all of you. That's what I like. And it looks like this. So let's talk about this. Let's talk about this curve. So in the vertical axis is the irradiance. We've talked about these units. It's in watts per area, per frequency, per angle. As you see. So this is watts is ergs per second. This is energy per time. And this is the surface area. Now I'm going to use centimeters most of the time. But meters is fine. Watts is fine. I like ergs per second. But, nanometers is the wavelength. And what's the radians is how much of the sky you see. So this has several useful features. The most useful feature is that the peak wavelength drops with temperature. So all I need to do is measure the frequency distribution coming off a star, find the peak, and then I know the temperature of the star. Does that make sense? That's incredibly powerful. Further, I don't even need to do that. Because, for instance, like if we look at this big 7,000 Kelvin star, so do you know the surface temperature of the sun? 5,777. So it's like 6,000 Kelvin, 5,000 Kelvin. And it peaks in the visible wavelength. But a hotter star, a more massive star, will have a temperature of like 7,000 Kelvin and will peak in the blue, or maybe even bigger than that, they might peak in the ultraviolet. So measuring the peak is pretty tricky. But the other thing that's super helpful is the slope here is directly related to the temperature. So that's all I need to measure here.
So if star peaks in ultraviolet, what does that look like from our perspective?
It would look blue. They look pretty blue.
I was curious.
Because most of the light is still over here.
Okay.
So they look pretty blue, but you can't see the rest of the star.
Is it ever possible for them to peak in like gamma? Or is it like only supernova?
I think that for it to start peaking in the high ultraviolet into the X-rays, you start to get towards the Planck energy. So at some point you can't be that hot because you get more than a Planck energy in a Planck light if it's going to peak into gamma. But we can sort it out from this. What temperature would that need to be? What's the wavelength of a gamma ray? It's like 10 to the minus 15, right? So the temperature would have to be like 10 to the 15 Kelvin, which is untractably large. But that's an interesting question. So, in principle, it can peak wherever. It runs out of quantum mechanics. Yeah.
So can an object give off both line radiation and black body radiation, but it's not a black body?
Then it would be a black body plus something else. So like this. So here's a spectrum from a bunch of stars.
Oh, sorry, I thought the black body said you can't have line radiation.
For the black body doesn't have line radiation. But the spectra can have both in it. Is there? Do you know where the light switch is? I want to clip the lights off real quick.
Fine, you can, by the monitor.
Oh, sweet.
Oh, I
Can I clip
can't
just
see
the front
past
ones
your
off?
computer.
Okay, that makes that a little better. If I can kill that one. That's better for this though. So what do we see? We see the color resolution of this projector is not very good. This looks way better on a laptop. But you can see that it's brighter over here. For these stars down here, it's brighter over here. And for these stars over here, it's brighter over here. So you see, if you just look at this yellow strip, it gets dimmer as we go up. Because these are stars that are ranked in order of their temperature. So the hottest stars are at the top and the coolest stars are at the bottom. The ordering of star temperatures goes O, B, A, F, G, K, M. And that's how we classify stars. I'll talk more about this in a little bit. And why it's not A, B, C, D, E, F, G, because the discovery came before the understanding. We do that a lot. So sometimes things are named really dumb in astronomy. Sometimes totally backwards. Sometimes in just a random ass order. Because we discovered things and then understood what they were doing later, but didn't go back and fix the nomenclature. So stellar classification, O, B, A, F, G, K, M. Those are just types of stars. For now, they're types of stars. But you can see the black body looks so much better on my napkin. So that the light peaks over here for this hot star and over here for these cooler stars. In addition, you can see these black strips. These black strips are lines. So a star is a black body, and then it's got an atmosphere above it that absorbs stuff. And those are the lines before. I'll talk about lines in a second.
So it has both a black body and something that's emitting
That's
line
right.
radiation, but they're different parts of the object.
There's different parts of the object. That's exactly
Okay.
right. So the black body function looks like this. So it's 2hc squared. I don't care about those, they're just constants. Lambda to the -5, e to the hc over lambda kt minus 1. Or if you write it as a function of frequency, you pick up an extra factor of c squared. So you get lambda to the third c squared. If you just plug in lambda equals v over c, you don't quite get the right answer. You got to do it a little differently. I'll show you that later. B nu is nu cubed over e to the h nu over kt minus 1. So this h nu over kt is the photon energy over the thermal energy. And it's really key. That's the same thing that you get here. It's the same. This is h nu over kt as well. The denominators are the same. The only difference is how many lambdas you get. You get 5 lambdas or 3 nus. That comes out of details that I don't care about. So, does everybody remember what a Taylor series is? Does anybody want me to remind them what a Taylor series is?
Yes.
All right, sweet. Let's do that. Lights. Let's put the lights on so that I don't fall asleep. So, let us talk about Taylor series. When I learned what Taylor series was, I thought it was the stupidest thing I've ever heard in my life. Because you have this function, and you can define it with this far more complicated thing. And I'm like, why the hell would you want to do that? It seems so dumb. But then I started studying physics, and I realized that making everything look like a line is really what you want to do with your life. So if I have some function f of x, right, it's something complicated, I want to approximate it. So the reason that we use Taylor series is so that we can throw out a lot of crap and get rid of and take functions that are horrible and I don't know how to integrate and turn them into functions that are not so horrible that I do know how to integrate. So this thing here, the black body curve, that's a difficult function to integrate. It can be done, as you will see on the homework. You can integrate that just fine, but like partial integrals are difficult. So if I want to just integrate part of it, that thing is hard to use. But the other two are easy. So how do we get that? So I'm going to make an approximate function. So that equals, we got to approximate at a point. So we're going to pick a point. Let's call it here. We call that x naught. So I'm going to approximate this with various kinds of polynomials. And that's why it gets useful, because I know how to do math with polynomials, right? Polynomials are super easy to deal with. sines and cosines and exponentials, sines and cosines anyway, are super tricky. And then these complicated algebraic things are horrible. So we're going to say that it is equal to f at x naught, but I'm not at x naught, so I know that. But I want to know x naught plus delta, where delta is something small. This is equal to f naught plus x naught minus delta times f prime of x evaluated at x naught. It's a little horrible way to say it. Sometimes you'll see this f prime of x naught. It's a little bit more accurate to say it the other way, but this works fine. So what is this? What is f prime at x naught? This is the derivative. So x times f prime, or delta times f prime at x naught is the slope here. Right? And I can add another term plus, we'll just write down the whole series, x naught minus delta to the n over n factorial times f, and the nth derivative here, we'll write this as dnf dxn. So this is how you define a Taylor series.
What's
Remember
the denominator that starts with n?
n factorial.
Okay.
That's a bang there. So, if I take this and if I take the black body and I do a Taylor series expansion on the wavelength, so I say that the wavelength is small compared to hc over kt, or I can do it in the frequency, both are fine, but I'll make you do it in the wavelength so that you can get the Rayleigh Jean. So if I assume that lambda is long, then I get this value. If I assume the lambda is short, then I get this value. So you do a Taylor series of that, and you get these two approximations. One of them looks like this. So, and we can look at it. So this one looks like t over lambda to the fourth, right? So that's an increasing function. So Rayleigh Jeans is down here. So this bit here looks like t over lambda to the fourth. And the long way, the long way. This is t over lambda to the fourth. I should have known that this was wrong because 1 over lambda to the fourth is a decreasing function of lambda. But this goes up, right? This is decreasing over here. And then over here it looks like an exponential. On the short wavelength you get e to the minus hc over lambda kt over lambda to the fifth, and that's this side here, so you get some exponential. And the exponential wins and makes it go up. Okay. Now these two things are easier to do math with than this, which is part of the reason why they're still used. Some of you had asked if they're still used. Yeah.
How does that include the Planck constant if it was before Planck?
This one doesn't.
Like
And
H?
this one, they just left it as constant at the time. Right now it has the Planck's constant because I put it in there. It was just a number before. It was just some fit constant beforehand. Now we understand that that has to be Planck's constant. But that's a good question. I don't know a ton about how all this developed. I'm sure that it was great fun.
Was the number similar?
Ultimately, they were getting similar numbers. I mean, they all orbited and then converged on the same number. What's that? What do you think?
Planck just got his name on it, because he just said, okay, it's gonna be a constant.
Well, he was the one that was like, no, okay, this is the number that matters. We want to use that number. I mean, it was. They weren't getting the same number. They were getting hc squared. So they're gonna be off by c squared, which is a big number.
Yeah.
So, hard to say how so I don't really know how it all developed, but it was complicated. Yeah. Taylor series. Okay, so now, what's the total luminosity? This is the thing that we want to know, and we're going to get the total bolometric luminosity. So think about the units for the black body. Give me this. No, you. Okay. Now I want ergs per second. And I'm going to get rid of the denominator by integrating. Does that make sense? So an integral is like multiplying or adding. So I need to integrate out this centimeters, which is the wavelength. We'll do that last. We've got to integrate out this centimeter, which is the area. We'll do that first because it's easy. We've got to integrate out the steradians, which is where the photons are going off the surface. So this idea is we're looking at a star. The star per unit everything emits like a black body, but we need to actually incorporate the geometry of what a star looks like. So the first thing we do is integrate over area. So, and the book does all these at once, but that's kind of horrible. So we've got b nu of t, which does not depend on any of my spatial coordinates. So I've got a star. And we're going to describe it with phi, theta, r. Right? So those are the coordinates that define the star. Then I need to define the coordinates where the star is radiating off from. So I've got another little coordinate system on the surface, and I'm going to call this phi prime, and I'm going to call this theta prime. This is a secondary coordinate system that I'm on the surface. So we're going to do that one first. Actually, let's do the area first because it's easy. So we need to integrate over area, dA. And what does the area look like in spherical coordinates? The area looks like r, sine theta, d theta, d phi. Why is that? So if I think about what the surface area, so thinking about tiny little elements. So I'm just going to draw rails of constant radius and then look at what the volume is around those rails. So think about this as square. And in here is my volume element. So it's going to increase like r. It's going to increase like sine theta. Uh-oh. Sorry. I wrote the wrong one. I'm using the mathematician's phi and not the physicist's phi. Doesn't make a huge difference. Just do what I said. So this is sine of the polar angle times d theta d phi. So when I integrate this, so phi goes from 0 to pi and theta goes from 0 to 2 pi. And when I do this whole integral, all I'm left with is 4 pi. Oh, that's going to be squared. Is a 4 pi times r squared. And that's it. That's the surface area of a sphere. So the first integral, I just pick up a 4 pi r of the star squared times b nu. So we're going to call this integral 1. So we've integrated out just the surface area. Now this becomes very important in a second. So the second thing we need to do is integrate out, so that's adding up all the points on the surface. Now we need to integrate up all of the ways that it can shine into the sky, which seems a little like dumb because didn't we already take care of that? We didn't. And this one's kind of hairy. So if I think about a plane like this, what I actually need is a cosine of this and then the volume integral element. So I have another polar integral. This one goes from 0 to pi, and this one goes from 0 to 2 pi. But there's an additional cosine theta because what I'm thinking about is, if this is my surface, we'll pretend it's flat for a second. This ray, or if I'm say I'm shining a light onto a surface, it's the same as if the light's coming off, but it's easier to get your head around this way. Say the light's shining on the surface. This one is going to shine with an irradiance I. This one is going to shine with an irradiance I cosine theta, where the angle here is theta. Does that make sense? So as I turn my flashlight, the light gets dimmer. It's just like the sun going down or whatever. But I need an extra cosine theta in here. So then when I do this integral, all I'm left with is pi. Okay, it's horrible, it's hard to get your head around, but it just gives you a pi. The pi is important. I got a cartoon of this. This is from the book. This is the cartoon that the book is using. Oh, and he used phys. So my phi and theta are reversed on this board. Feel free to forget everything that's up there. So this is the cartoon of how you're doing the integral. So I've got a little patch here. My radiation is coming off of that patch. It's got a little solid angle, a little angle here. So this is, if I move r and theta around, this is how a tiny little patch changes with r and theta. That's what this diagram is showing. So here, what I've done is I've integrated out the steradians and I've integrated out the area. I just stole this from the book. So we get what the book calls the monochromatic flux, which means the flux at one frequency. So this is the total flux as a function of frequency. So I've gotten rid of all the geometry. That's the important bit. And I'm left with this, 4 pi squared r squared times b lambda, or if I plug everything in, I get all of this. Does that make sense so far? And the last bit is I need to integrate over wavelength. So I have this function here, and I need to integrate over wavelength. Somebody way smarter than me sorted this bit out. So you just take this integral and you make it look like this. And you're left with the total luminosity looks like this. Luminosity is 4 pi r squared sigma. The other pi goes into this sigma. All of the rest of the constants and crap go into this sigma. The sigma is called the Stefan-Boltzmann constant. And then T is the effective temperature to the fourth. We call it the effective temperature. Just treat it like the temperature for now. So, because ultimately temperature, when you get really existential about it, gets hard to actually define. So you can ignore the fact that it says effective. It's just the temperature of the star. Yeah.
What is x in that integral?
This? Oh, this is just a dummy integral.
Yeah, but like, what is it? Dummy integral.
Well, this is just a statement of fact.
Okay.
This integral from 0 to infinity of x cubed over e to the x minus 1 dx, is pi to the 4th over 15. So the second question that you hadn't asked yet is, how do I use that to actually solve this? So you see how this is an e to the some crap minus 1? You just do a u substitution on this. So I integrate this from 0 to infinity. I do a u substitution to make it look like this integral, and then this falls out. Because when you do this integral, if I integrate this over wavelength, then I'm left with a total bolometric luminosity. Does that make sense? This will be a homework problem just because I think it's really valuable for everybody to sit down and do it, even though I just went through it. It's worthwhile to put your hands on this and see where all the pieces come from, even though it's a little messy. How am I on time? Oh man, I'm almost out of time. Okay, I didn't get to colors yet. Okay, I'm gonna go really fast. So if I, instead of wanting the whole thing, I just want part of it, okay, how do you make a spectrum? So this is a spectrum. This is all of the light based on wavelengths, but how do I make a spectrum? Well, to make a spectrum, say I want a spectrum of this star right here, this guy. I take my telescope, and I point it at Andromeda, and then I take a giant metal plate, and I put it in front of the image. And that makes a diffraction grating. And that diffraction grating then smears the light out into a spectrum. Now you see I covered up the whole picture, right? That's what they do. So if I want to get a spectrum of a star, I got to have a lot of CCD real estate. And I don't necessarily want that, because that's a pain in the ass, because it's very difficult to make a lot of spectrum. Now sometimes I do want it, and so we'll go through the effort of taking spectra for everything, but it's tricky. So sometimes what I want, remember how I said the slope of the line right here is also directly dependent on temperature. So I don't need to measure the peak, I can measure the slope of the line here, in this region. Does that make sense? How do I measure a slope? What slope? Rise over Right. Slope is rise over run. Always. It's always rise over run. Now you take the elements and make it tiny, and that's when you have the derivative. But I just need the slope here, so I just need to measure the flux at this point and the flux at this point, and I want to do it for a whole bunch of stars at once because I want to know what all the temperatures of all the stars in the globular cluster are because there's a million of them, and I want all of them. So we'll use filters for this. So is this my filter deck? My filter deck. There you are. So here is a man plugging in fiber optic cables into a big plate at the Sloan Digital Sky Survey so they could do spectra of a whole bunch of things at once. Very cool thing, very labor intensive. So what we want to do is just look at sections of this spectrum at a time. And we do this with colored pieces of plastic. It's really cheesy, but we get very specifically designed colored pieces of plastic. And these pieces of plastic take our black body, and what we can do, what we can do is say, okay, I got my so I have my spectrum versus wavelength. I could just cut this part out and ask how much light is in this part, and I'll make that small, and then I'll cut this part out, and I'm going to call this one B, and I'm going to call this one V. And then we'll take the difference. But I'm out of time, so we'll come back to filters on Monday, and that's it. Nothing else is, no, there's some stuff on Monday.